The definite integral, a graphical interpretation. When discussing the graphical interpretation of the definite integral, we use the term signed area. And signed area means the area above the x-axis minus the area below the x-axis. So we have this function here, let's call it f of x. And when we talk about the signed area, in terms of the definite integral, we're talking about the area that's above the x-axis, so between the curve and the x-axis, and then minus the area that's below the x-axis, so between the curve and the x-axis here. So signed area is the combination of these two. So we think about the area above the x-axis as positive, basically, and the area below the x-axis as negative. So the definite integral, the integral from a to b of f of x dx, is the signed area of the region between the graph and the x-axis on the closed interval from a to b. So for this particular graphical example, we can see that the total signed area, the definite integral from a to b, so 0 to 6 of this function f of x, it would be a net positive value because there's more area above the x-axis between the curve and the x-axis than there is below the x-axis. Let's go ahead and take a look at an example. So here we want to calculate the definite integral from 0 to 3 of the function 2x minus 5 with respect to x using the interpretation of signed area. So what we're going to do is start by graphing 2x minus 5, which is a linear function. So we want to sketch an xy plane here. And we want to try to be as accurate as we can. So we're going to draw the y-intercept, try to make these evenly spaced. The y-intercept is at -5. And then the slope is positive 2, so up 2 over 1. So we have up 2 over 1, that would bring us to -3, 1. And then another up 2 over 1, that would get us to 2, -1. And then if we go another up 2 over 1, that will lead us to 3, +1. So I'm going to go ahead and sketch this line. And I'm only going to focus, though, so I'm going to erase a little part of it. I'm only going to focus on the line between the x values 0 and 3. So I'm going to do like a little bit of erasing here. I'm going to erase this little portion here. So here's my linear function. When we talk about the definite integral, we're talking about the signed area. So the area that's trapped between the function and the x-axis. So I'm going to go ahead and highlight the area that is above the x-axis. I'm a little bit over because my highlighter's so big, but we're talking about this little triangle right here. Let's see if I can do a little erasing. So we're talking about this triangle right here would be considered positive area. And then we have the part below the x-axis, so between the curve, or in this case it's a line, the line and the x-axis, it would be this triangle here. And so notice how they form these perfect geometric shapes, right? So we have just two triangles that we're essentially trying to figure out the area of. So I want, the area above the x-axis minus the area below the x-axis. Well, the area above, as we said, is a triangle. And so the formula for a triangle is 1/2 base times height. So here's what we're going to do. So the integral from 0 to 3 of 2x minus 5 dx is equal to 1/2 base times height. So you know what, I'm going to make it green here to indicate that green portion. So 1/2, and then I need base times height. Well, I can see the height is 1 here. So right, if I think about where that coordinate point came from, I went up 2 over 1. So the height is 1. But what's the base, right? Well, I tried my best to be as accurate as I could here, but ultimately we need the x-intercept. Like I need to know where this graph crosses the x-axis to be sure of what this width right here is, right? Like of that little base of the triangle. So finding the x-intercept, we could pretty much do it in our head, but I'll just go ahead and write it out. It's setting the function equal to 0. That's how we find x-intercept. So if I add the 5 and divide by 2, I get 5 over 2, which is 2.5. So my graph wasn't perfect. It doesn't look exactly like 2.5, but it turns out it is. So if this point right here is 2.5, then that means that the base is 0.5 or 1/2. So this is the area that's above the x-axis. It's a geometric shape, so we can find its area exactly. We're not approximating it. So 1/2 base times height. And then we have to do minus the area of the triangle that's below the x-axis. So we're going to have minus, and then it's 1/2, again, base times height. Well, the height of this triangle is 5, right? So it's 5 units tall. I can see, the y-intercept was -5. So total, when we're talking about heights, we're going to use +5. So base times height is 5. And then the base goes from 0 to 2.5, right? Which was 5 over 2. So this right here, I'm going to leave it as a fraction just because all fractions are currently involved. So we have the area of the triangle on top minus the area of the triangle on the bottom. And then we just go ahead and simplify here. So we have this is 1/4 minus 25 over 4. And so that's -24 over 4, which simplifies to -6. And so notice we have a negative answer in reference to area. And that's because, again, we are defining this signed area as the area below the x-axis is negative and above the x-axis is positive. So if you look here, we knew our answer was going to be a negative number. There's more area below the x-axis than there is above the x-axis. So we knew the answer was going to be negative. So it's kind of a different concept that we're used to. We're used to thinking about area as only positive. If we're finding the area of a square, it's positive. But now it's got a different definition when it comes to a definite integral. It is possible to have negative area because we consider that the area that's below the x-axis. In this next example, we're going to calculate the definite integral from -1 to 4 of the absolute value of 3 minus x dx using the interpretation of signed area. So here we have this absolute value function, absolute value of 3 minus x, and we want to go ahead and graph it. So let's just take a second, though, to work with the equation a little bit to maybe make it easier to graph for ourselves. So the absolute value of 3 minus x, that's the same as -x plus 3. I'm just switching those places, the commutative property. And then I could factor a negative out. So I took a negative out of each term. And now the absolute value bar, or absolute value, makes this negative a positive. So it turns out I have just the absolute value of x minus 3 is the same as the absolute value of 3 minus x. So the reason why I did that is just because we're used to graphing the absolute value of x. That's the function that looks like a V shape. And then this is just a quick transformation. This is going to shift everything to the right 3 units. So I just thought I'd write it like that instead so we can use transformations to graph it a little bit quicker. And so we want to graph this thing between -1 and 4 because those are the limits of integration. I'm skipping a number. -1 and 4. And so it has that V shape. It has that V shape, but everything moves to the right 3 units. So normally it would go through 0, 0 as its vertex, but now its vertex is 3, 0. Everything shifted to the right. And then the slope is 1 and -1 for each of those pieces of the V. So like up 1 over 1. And then here, like left 1, up 1, left 1, up 1, left 1, that was a little bit off. Left 1, up 1 is going to take me to 3. And then same thing, left 1, up 1 is going to take me to 4. So I know I have this V shape here with the slope of 1, and I only graphed it Okay, I'm not too far off. Here we go. I only care to graph it between -1 and 4 because those are my limits of integration. But obviously the entire graph of the absolute value of x minus 3, it keeps going. But I don't really have to care about that. I'm interested in the area between x equals -1 and 4 of the absolute value function and the x-axis. So I'm going to sketch that area here. So it's trapped between, again, the curve and the x-axis. So these are the two regions that we're going to try to find the area of. They're both positive. So we know that our overall answer to this problem is going to be a positive value because there's no area that's below the x-axis on this one. So we have the integral from -1 to 4 of the absolute value of 3 minus x dx is equal to, again, the area of two different triangles. So our triangles formula is 1/2 base times height. So we have one triangle over here with a base of 1, 2, 3, 4 units. Don't forget that 0 is right there. So we have 1, 2, 3, 4 units is the base, and then 4 units is the height. That's the highest point there. So 1/2 4 times 4, that's the area of this triangle right here. And then plus, so we're not going to subtract because we're not below the x-axis. We're going to add this other triangle, which is 1/2 a base of 1. The distance between 3 and 4 is 1. And then the height of this triangle is 1. So we just add those two together. So here we get 16 over 2 plus 1 over 2. So we end up with 17 over 2 as the exact area, or if you prefer decimals, 8.5. And again, we knew the value was going to be positive because all the area was above the x-axis. Now we can only use the interpretation of signed area to evaluate a definite integral if the region between the graph and the x-axis is a geometric shape that we have the formula for. So we have the formula for finding the area of a triangle, and so far we've just dealt with a bunch of triangles. In this example, we want to calculate the integral from 0 to 2 of the square root of 4 minus x squared dx using the interpretation of signed area. So the first thing I want to look at is the integrand, the square root of 4 minus x squared. And I want to point out there's a very common algebra mistake that people try to do. I'm going to do it in red and then cross it out to show that it's incorrect. People try to simplify this, the square root of 4 minus x squared, to be 2 minus x. That is not true, right? Absolutely not. This is not true. So I cannot take the square root of each term here because they're added or subtracted, and that's not a property of distributing the radical. So that's not what we're going to do here. We have to recognize that the square root of 4 minus x squared actually graphs a semicircle. And the radius of that semicircle is 2. So semicircle with radius 2, centered at the origin. So centered at 0, 0. So in general, just like for some reference, if you have y equals the square root of r squared minus x squared, that is the top of a semicircle with radius r centered at 0, 0. So here, that's exactly what we have. We can go ahead and graph it. So it's the top of a semicircle with the center of the circle at the origin, and the radius is 2. So that means all around I have that radius of 2. And this is not gonna, I don't think it's gonna fix nicely for me. So I'm going to do my best to make it look like a semicircle. Okay, there we go. So we have a semicircle with radius 2 centered at the origin. That's the function. Now I'm interested in the signed area between 0 and 2. So 0 here and 2 means that I'm interested in the area of a quarter circle. I'm interested in the area of this quarter circle right here. So we can find that the integral from 0 to 2 of the square root of 4 minus x squared dx is going to be 1/4, because a quarter is 1/4 of the area of a circle. Well, the area of a circle is pi r squared. The r in this example is 2. The radius is 2. So the area of a semicircle is 1/4 pi times, in this case, 2 squared. And it's positive because it's above the x-axis. And 2 squared is 4. 4 times 1/4 is 1. So all we have left is pi. So the answer to this definite integral is pi. Now, the previous three problems have all said calculate using the interpretation of signed area. But as we move forward in our study of integration, we would have to recognize when we can actually do this. So the reason we could do this interpretation of signed area on the last couple problems is because the functions themselves created these perfect geometric shapes that we have known formulas for. The area of a triangle, the area of a circle, so that we can cut it into quarters and find the area of a quarter circle. So we'd have to know what the functions look like, and that we are able to then use the interpretation of signed area. And there will be, for some problems, alternate ways to calculate these, but some there isn't. There is no other way to evaluate these except for understanding the graph and knowing those geometry formulas. So part of what makes integration tricky is that we're going to create this big collection of techniques, and we're going to have to know what techniques to use based on what the particular integral looks like. Now let's take a look at some properties of the definite integral. If we suppose f and g are integrable functions over the interval from a to b and k is a constant, let's see some of the things we can do. If we have the definite integral from a to b of f of x plus or minus g of x in the integrand, we can actually split it up to be two separate integrals, the integral from a to b of f plus or minus the integral from a to b of g. So we can split it up and evaluate each one separately if it makes the problem easier. In number 2, we have the integral from a to b of a constant k times f of x. That's equivalent to pulling the constant out of the definite integral. Assuming that constant is multiplied to the function, we can go ahead and pull it out. Number 3 tells us that the integral from a to b of a constant, just completely by itself, dx, is equal to this formula here, k times b minus a. So we're subtracting those limits of integration times k. I like to just show graphically what this represents, because it's like, well, where is this formula coming from? It's actually very intuitive if we draw the graph. We're looking at some function that's constant. So y equals k is that function. We're interested in the area between the x values a and b that's trapped underneath this function. Well, the shape that's being created there is just a rectangle, right? The area under a constant is just going to form a rectangle, and the area of a rectangle is base times height. Well, the height is k, and the base would be found, that length, by doing b minus a. So that's why that's the formula here. For number 4, we have, if you're given the integral from b to a of f of x dx, so that's flipped. We're used to a to b, right? And the whole idea being we want smaller to bigger. So if it happens to be flipped and the bigger number is on the bottom, so b to a of f of x dx, what we can do, a property of these definite integrals, is we can flip the limits of integration. We can make it a to b if we put a negative on the outside. So if we flip the limits of integration, it creates a negative in front of the integral. And again, that's if a is less than b. And we assume a is less than b because when we write intervals, we do smaller to bigger. For number 5, the integral from a to a of f of x dx is 0. Just thinking about that, it's common sense. If our integral starts at a and ends at a, there's no area there, right? There's no area there, so that's just 0. And then finally, the last one, if I have the integral from a to c of f of x dx, and b is trapped in between a and c, we can split up this integral to be the integral from a to b of f of x dx plus the integral from b to c of f of x dx. Now, this may look a little more complicated, again, than maybe the graph would help us understand. So I'm going to, once again, just sketch a little graph of what's going on. So imagine we have this a, b is trapped between it and c, and we have some random function. I'm going to just make it a positive function to make things easier to understand. If we're interested in the area from a to c, right, that would be all of this area between the curve and the x-axis here. If we're interested in this area from a to c, well, that's the same as going from a to b and then going from b to c. It's just collecting those two regions and adding them together. So that's seems a little more complicated when written out, but that's really all this is saying. Let's take a look at an example. Let's say we have find the integral from 2 to 2 of the square root of x squared plus 7 dx. So what a lot of students tend to do, and you'll notice as we move forward, the common thing is to just look directly at the integrand right here and start thinking about the different things I can do to the integrand. But if on this problem you did that, this is actually a really tough integrand to work with, but there's no need to do anything to it if you recognize that the limits of integration are the exact same value. Find the integral, find the area between x equals 2 and x equals 2 of any function, that's just going to be 0. So there's no work involved in this problem other than being observant and recognizing that the limits of integration are the same. So that must mean there's no area trapped between there, regardless of what the actual function is. Let's look at a few more examples that involve those properties of definite integrals. Let's say you're given these few pieces of information here. The integral from 2 to 0 of f of x dx is equal to 2. The integral from 2 to 4 of f of x dx is equal to negative 3. The integral from 2 to 4 of g of x dx is equal to 4. And the integral from 0 to 1 of f of x dx is equal to 1. So we have these little pieces of information about the functions f and g and the signed area between certain x values. So the signed area between 2 and 4 on the function f happens to be negative 3. So we just have some sort of random pieces of information. Now, before we move on to the actual problems, I want to observe that one of the given pieces of information has the limits of integration flipped, as in the smaller number isn't on the bottom. So I'm going to choose to right away make the limits of integration go from smaller to bigger, from 0 to 2 of f of x dx. But remember what that's going to do? It's going to make the quantity negative. So since this was positive 2, that means that now that quantity is negative 2. So I'm going to focus on these 4 as my given pieces of information now, so that I don't worry about confusing myself later with this whole flipped limits thing. So we want to use these pieces of information and the properties of definite integrals to evaluate the following problems. So here we have the integral from 2 to 4 of 2 f of x minus g of x dx. Well, our properties tell us that we can split this up into the integral from 2 to 4 of 2 f of x dx minus the integral from 2 to 4 of g of x dx. So remember, if we have two functions that are added or subtracted, we can, in the integrand, we can split it into two separate definite integrals over the same limits of integration with respect to the same variable. So we need the dx in each one. Well, I have this piece exactly. I have the integral from 2 to 4 of g of x dx. That whole value happens to be 4. So I can essentially replace this whole quantity right now with just the number 4, and that's being subtracted. Here, the integral from 2 to 4 of 2f of x dx, I don't have that exactly. I have the integral from 2 to 4 of f of x dx. So what I have to do is use another property of definite integrals that tells me I can pull this 2, because it's a constant, out of the integral. And now I have exactly this quantity, the integral from 2 to 4 of f of x dx. That can be replaced with a -3. And then we'd bring that 2 on down, and we'd bring the -4 on down. So we end up with -6 minus 4. So we end up with a quantity of -10. So this was an example of using the properties of definite integrals, and it's not, these problems aren't just about getting this numerical answer, it is about showing the work correctly, where you are applying the first property, where we can write it as two separate ones, very formally including the dx, that first we have to pull out the 2 before we can make this replacement. So it's about understanding and showing the proper usage of the properties of definite integrals. Let's take a look at this one here. Let's try to find the integral from 0 to 4 of f of x dx. Well, if we look at all of our limits, we have 0 to 2 of f of x dx, 2 to 4, and then 0 to 1. So those are all the ones involving f. And so we want the integral from 0 to 4. We don't have that exactly. We do not have exactly the integral from 0 to 4. So here's where we start to use one of our properties of definite integrals. And that property is the one where if we do happen to have a value in between 0 and 4, and two integrals that involve that separate value in the correct way, we can split this up. So this can be written as the integral from 0 to 2 of f of x dx plus the integral from 2 to 4 of f of x dx. So we don't know exactly what the graph looks like, and this is just to help briefly illustrate the concept. But let's just say, f of x is this curve right here. I want the area from 0 to 4, and I have the area from 0 to 2, and I have the area from 2 to 4. Well, yeah, just add those two things together, right? And that's what we have. We have the area from 0 to 2. It was -2. So this whole quantity gets replaced with -2, plus the integral from 2 to 4 was -3. So total, we get -5 as our answer. So clearly this was not the correct graph, right? It was just a quick sketch, but the net area was negative, and the random graph I drew is obviously positive area. But just to illustrate how and why we can break it up, into these two pieces. Okay, so now the final part here is find the integral from 1 to 4 of f of x dx, from 1 to 4. So keeping with this sketch I drew up here, I'm interested in the area from 1 to 4. So let me use a highlighter for that. I'm interested in this piece right here. Well, in the previous part, I found all the area from 0 to 4, so I have all of this, but what I would need to remove is this chunk right here. I want to get rid of everything from 0 to 1, and I only want to be left with everything from 1 to 4. Well, we have that information. We know that the area from 0 to 1 happens to be 1. So in other words, we can rewrite this definite integral as the integral from 0 to 4 of f of x dx. So what's that doing? It's finding everything, right? Which we did in the second example here. We found all this area, but then I want to take away the area from 0 to 1 of f of x dx, which again, we happen to have was 1. So this piece was given as positive 1, and then we found the integral from 0 to 4 in part B. So we're going to use that value. That's -5. So -5 minus 1 is -6. So this wasn't, the correct graph for f of x, but it was enough to help understand the concept of how we're going to use the given pieces of information to rewrite these using the properties of definite integrals. Now, in talking about the definite integral in terms of its graphical interpretation, if we can use symmetry on the function, that would make our lives a lot easier if the function had symmetry. So before we start, let's just remember some information from pre-calculus, the idea of an even and odd function. So remember, a function is even if f of negative x is equal to f of x. So I always used to say even functions eat the negative. So when you plug in a negative x, it just disappears completely. Or graphically, there is y-axis symmetry. So an example of an even function, so if I have an even function, an example of an even function is something like x squared. So y equals x squared has y-axis symmetry. I can fold this graph over the y-axis and it's exactly the same as a mirror image over the y-axis. A function is odd if f of negative x is equal to negative f of x. So what's happening here on an odd function, when you put a negative into the x, it spits it out. So odd functions spit out the negative. And in terms of the graph, a function is odd if there is origin symmetry. So by origin symmetry, I will do an example. The function x cubed, y equals x cubed, has origin symmetry. So that means if we rotate this graph 180 degrees, so spin it 90 and then another 90, and you put it right back down, it looks like the exact same function. So this is an example of a graph that has origin symmetry. This is an example of a graph that has y-axis symmetry, right? So it's called even and odd. Now let's take that and apply it to this idea of definite integrals, if possible. So let f of x be continuous on the symmetric interval negative a to a. So what's important is the only way we can apply these properties or these rules is if the limits of integration go from negative of a number to positive of that same number. So if those are the limits of integration, we might want to keep this in the back of our head, like, oh, is the function even or odd? Because that might make this problem easier. So if we have that symmetric interval, and if the function is even, and we're trying to do the integral from negative a to a of this even function f of x dx. So think of this y equals x squared that I have drawn over here for a second. This is an even function. If I'm interested in the integral from negative a to a, that would be this area here and this area here, right? Assuming it's symmetric, so these are supposed to be, the same value on each side. Then instead of finding the area from negative a to a, an alternative, an option, would be to find the integral from 0 to a instead. So let me erase this. Let's go from 0 to a, this part right here, and then double it, right? 2 times the integral from 0 to a. Because if there's y-axis symmetry, that area under the curve on the right side from 0 to a is going to be the same. So we're just going to multiply it by 2. So this only works if we have a symmetric interval, negative a to a, and if the function is an even function, that we could apply this sort of shortcut technique. So that's the first property that we look at here. And the second one is, well, what if f is odd? Right, so let's move this back away for a second. So what if f is an odd function, and we're going to do the integral from negative a to a of f of x dx? Well, it's super nice. This is a really nice property, or just concept, really, that the answer is just 0. And so let me pull up this odd function that I sketched a second ago, x cubed. So again, let's say we're talking about the integral from negative a to a. So remember that the definite integral is signed area. So we're talking about this area here above the x-axis to the curve is positive. And then from negative a to 0, we're talking about the area below the x-axis is negative. So they're the exact same amount of area, but one's on the top and one's on the bottom. So they're going to cancel each other out on an odd function and give us 0. They're going to cancel each other out and give us 0. So these are kind of just nice to have, again, in our toolkit for evaluating some definite integrals. So again, we're looking for the symmetric interval and then either an even or an odd function. Odd would be ideal because then the answer would just be 0. So let's take a look at one example of this. We're told to calculate the definite integral from -2 to 2, there's a symmetric interval, of x times cosine x dx using the interpretation of signed area. Now, here you might think about that as, oh, I have to graph it. I have to graph x cosine x, but that's not a basic function. That's not a function that you would be expected to know what the graph of that looks like, right? X times cosine x. No, if it were 2 cosine x, then sure, we should be able to graph that. But x times cosine x, no. But when we think about the interpretation of signed area, we can at least think about, and especially since the limits of integration are symmetric, whether or not this function is even or odd. So from pre-calculus, again, if I have a function, so I have x cosine x is the function, let's see what happens if I plug in a negative x. So that would give us negative x cosine of negative x. And cosine of negative x, well, cosine is an even function. So cosine itself, I'm going to just like sketch, let's see if I can fit it somewhere. Down here, I'm just going to quickly sketch a cosine function. Looks like this, right? So cosine itself is even. It reflects over the y-axis. And remember what I said, even functions eat the negative. So cosine of negative x is actually just cosine of positive x, because cosine itself was an even function, so it just ate that negative right up. But this negative in the front would stay there. So what we have is that f of negative x, when I plugged in a negative, I got negative of the function out. I got negative the original function. So I have negative x cosine x left over. So x times cosine x is an odd function overall. So cosine was an even function, which is why this negative x disappeared, but the negative x in the front didn't disappear, which means f of negative x is equal to negative f of x, which makes it an odd function. So because I have an odd function, so the integral from -2 to 2 of x cosine x dx, because this is odd, and because this is a symmetric interval, I need both in order to say this next conclusion, the answer is just 0. So whatever the graph looks like, and again, this right here, this is just the graph of cosine x. It's not the graph of x cosine x. Whatever the graph of x cosine x looks like, it's odd, and therefore the answer is going to end up being 0. Now, because we have technology at our fingertips, let's actually look at the graph. This is the graph of x cosine x. I've zoomed in on it, right? It actually looks like this, but closer to 0, because we only cared about what was going on between -2 and 2, we can see that we have an odd function. If I rotate about the origin, it's going to look exactly the same after rotating 180 degrees. We can also see how the right regions would cancel. So like the part that's right here from -2 to, you know, whatever this is, value like almost like -1.5, this is above the x-axis. It's going to cancel with this little wedge right here that's below the x-axis between like 1.5 and 2. And then this region that's below the x-axis from like -1.5 to 0 is going to directly cancel with the area above from 0 to 1.5. So we didn't have to know what exactly the graph looked like, but we did have to show through our like past pre-calculus methods and knowledge that we had to know it was an odd function in order to use that property. And again, because of the symmetry involved. So if we were going from -2 to 3, now the answer is no longer 0. A lot of stuff cancels, right? Those two little almost triangular wedges, and then these two little pieces would cancel. But you know, it wouldn't cancel everything from 2 to 3. So if our integral went from -2 to 3, now the answer wouldn't be 0, it would be some negative value. It would be whatever the area is between 2 and 3. So again, we're just making that connection in this section to the definite integral representing that signed area, and then different techniques that we can use, like geometry formulas, if it forms an exact geometric shape that we know the formula for, or If it doesn't, if it's a curve, is that curve even or odd? Can we use some other strategies to help us evaluate it?